All right, open up your book to section 10-5. We're on page 522 in your book. The title of this section is Analytic Geometry of Conic Sections. The objective is, given the equation of a conic section, find the foci or foci, pronounced both ways. That, by the way, is the plural of focus. We want to be able to find the directrices, that is the plural of directrix, and the eccentricity, and vice versa. So these are some new terms we'll have to talk about here in this section. We'll define each of those. But before we get going too far, you should have a copy of this handout here, which is the conic section properties. Definitely have it printed out there. There's some properties here that we'll definitely be using as we go through this section, but there's also space to sketch in the information relating to each one of these conic sections here. So make sure that you've got that printed out. That will definitely be helpful as we go through these notes. All right, so let's start with the ellipse. And I'm going to give myself plenty of space here to sketch this ellipse and all of the parts with it. You're going to want to do the same thing here. So like I said, if you've got that packet handy to write on, that will be ideal. But otherwise, make yourself a big sketch here of an ellipse. All right, let's mark a couple of key things here on this sketch that we've got here. First of all, the two lines that you see sketched, those are the two axes of our ellipse. Those are lines of symmetry, actually. We call the shorter one the minor axis. So I'm going to write that up here. This is called the minor axis. In this case, it's vertical, but obviously it could change here if I change the shape of my ellipse. And the longer one of the two is called the major axis. So this line right here is called the major axis. Oops. And in this case, it is horizontal, but obviously that could change there if I change my ellipse slightly. All right. Along the horizontal axis, along the major axis here, we have a couple of key points that we mark. First of all, the one right here in the middle, we call that the center of our ellipse. And if we travel down the major axis, I'm going to say somewhere about here. I'm just making a guess of approximately where that's at, but we have what we call the focus. And it turns out with an ellipse, you actually have two foci. They are equidistant there from the center, so I'm going to try to approximate those in the same spot, but about right here is my focus on the left side. You also have what we call vertices. The vertices are at the location where the major axis intersects the ellipse, so this would be a vertex here. And we would have a vertex on the other end as well. Notice that we have vertices on the major axis, but not on the minor axis. Even though the minor axis does intersect, we don't call those vertices. And then finally, we have two, in this case, vertical lines that we're going to draw. They're going to be perpendicular to the major axis is actually what I'm sketching here. But I've got a vertical line right here we'll sketch in. And that right there is what we call a directrix. And the same thing happens over here on the other side. Draw that vertical line in. Again, it is the same distance there, what I'm trying to sketch, the same distance there from the vertices and the focus and the center for that matter. This is a directrix. Okay. All right, those are the major components there, the names that we give to these different parts here. We are going to measure some different distances here along this, so I'm going to sketch those in here. So if I measure the distance from the center to the focus horizontally here, this distance right here, we call that the focal radius, and we name that C. So that's C. If we measure the distance from the center to the vertex, I'll draw that horizontally here, that distance right there, is what we call the major radius. We name that A. And finally, if we measure the distance from the center to the directrix, I'll measure that again horizontally right here. That distance right there is what we call the directrix radius, and that we call or label as D. You'll notice that we've skipped over B there in that process, and the reason we skipped over it is because when we measure the distance from the center along the minor axis, that distance right there is what we call the minor radius, and we label that as B. So there's our A, B, C, and D. And again, as you're looking at this sketch and comparing it with the information in that packet there, you'll see that these are labeled there appropriately and named appropriately on that packet. All right, one last thing I want to mark here is let's pick a point on our ellipse. So I'm going to pick some point. It doesn't really matter where it's at, but I'm going to pick a point right here. I'm going to label this as the point x comma y. That's some point that's actually on the ellipse. And I can measure a few distances. If I measure the distance from that point to my nearest directrix, that is this distance right here, that distance we call D1. If I measure the distance from that point to the closest focus, that would be this distance right here. We call that distance D2. And finally, if we measure the distance all the way over to the other focus, that would be this distance right here. We label him as D3. So there's what D1, D2, and D3 represent for us. Given any point x, y on our ellipse, I can make those three distance measurements. Obviously, as I change my point, those distances will change. The A, B, C, and D, though, those are set. Once you have your conic, once you have your ellipse there, A, B, C, and D are going to be set. All right, that right there is all the parts that make up our ellipse. Those are the things that you need to understand in terms of the names that we use to associate with the ellipse, as well as what these different variables represent. All right, let's take a look at the hyperbola. Hyperbola, just like the ellipse there, has a lot of stuff going on. So again, make sure you got plenty of room to sketch all of this. If you're using that packet that I gave you, you should have plenty of space there to write this. But if you're drawing this yourself, then give yourself a big sketch here of a hyperbola to work with. You'll see we've got a hyperbola that's opening up in the horizontal direction and the x direction. And the lines that you see sketched there, the diagonal lines, those are the asymptotes of that hyperbola. All right, so there's two axes that are marked here. Let's go ahead and label those. This horizontal one here, in this case, is what we call the transverse axis. It is the one that goes through the vertices. It actually crosses through our hyperbola. In this case, it's horizontal, but obviously I could have this hyperbola opening up in the y direction, and in that case, the transverse axis would be vertical. The other axis that you see here is what we call the conjugate axis. So in this case, that's vertical. It is perpendicular to our transverse axis. It goes right through the center of our hyperbola. All right, along your transverse axis, we have some key points that we mark and name along the way. So let's start right here in the center. This point right here where our asymptotes and our two axes intersect each other, that is called the center of our conic, the center of our hyperbola. If you travel along the transverse axis here, the first thing you'll hit here is what we call our vertex. And just like with the ellipse, there's actually two vertices. So if I travel in the other direction, I'll hit this vertex over here. So there's two vertices. And if you keep traveling in each direction, you'll hit somewhere about, we'll say about right here maybe. We have a focus. And there is symmetry about this, so that focus that I draw on the other side, I'm going to try to get it about the same distance here. Okay, somewhere about there we'll say is the focus. And then finally, you do have directrix with a hyperbola. It is perpendicular to your transverse axis again. Just like we saw with the ellipse, it's perpendicular to the major axis. The directrix, though, actually is between the center and the vertex. So you actually have a directrix that maybe is about right here, we'll say. This is a directrix. And we'll draw in the other directrix. So again, there's symmetry to this, so I'm going to try to draw it about the same, but you may be able to sketch yours. So there's some nice symmetry there. Okay, so those are two directrices here for the hyperbola. All right, let's go ahead and label a few distances that we need to know. In particular, we have these values of A, B, C, and D again, but we do give them slightly different names here because of the fact that we're dealing with a hyperbola. If you measure the distance from the center, horizontally in this case, to the directrix, that is our directrix radius, so we call that D, just like we did with the ellipse. If you measure the distance from the center to the vertex, which I'll draw this way horizontally, that distance there is the transverse radius, and so we label that as A. Notice it's the transverse radius as opposed to the major radius, like with the ellipse. And then finally, if you measure the distance from the center all the way to the focus, which I'll mark as this, that distance is C, our focal radius. And again, you'll notice there that we've left out this value of B. So the way to mark B, or there's actually a couple ways you can mark B. I'm going to mark it this way. If you start at the vertex and you go vertically to the asymptote there, that distance there is B. Or if you want to mark it along the conjugate axis like we did with the ellipse, then you'll have to kind of draw a horizontal line over here. This distance right here would be that distance B. Okay. All right. Lastly, let's pick a point, x, y, and we'll put it on our hyperbola here. It doesn't really matter where we pick it, but I'm going to pick this point over here. I'll call him x, y. And we're going to measure some distances between that point and our different parts that we've marked here. So let's first measure the distance from that point to the directrix. So that's this distance right here. We call that D1. If we measure the distance from that point to the closest focus, that's this distance right here. We call that D2. And one that's going to be, I guess, hardest for me to sketch because it's going to kind of cut through everything. But if I measure the distance from that point to the other focus, so that's going to be this straight line distance right here. That distance we call D3. I'll label him right here. So again, if you look at the information on your packet there, it's got all these different variables in there. This is what they're referring to, these distances here. Again, D1, D2, and D3 will change as you move that point x, y, but there's some nice relationships between those. The values of A, B, C, and D are defined once you have your conic, though. Those don't change. That right there is the sketch of a hyperbola with all of its parts clearly labeled. All right, those are the toughest two to sketch. The next one here is the parabola. I say it's the toughest just because there's the most stuff to sketch in there. The parabola is actually pretty simple in comparison. Here we've got a parabola that's opening up in the x direction, the positive x direction, but of course this could open up in either direction as well as it could be opening vertically, but this is just how we've got it sketched here. The one line that you see there is what we call the axis of symmetry. Not a very interesting name that we give the one for the parabola, but nonetheless, that's what the name is the axis of symmetry. A parabola doesn't have as many parts to it as we saw there with the ellipse and hyperbola. First of all, there's no center to this, and instead what you have is a vertex. So I'm going to go ahead and mark that vertex right there, and we'll label him. That's our vertex. You do have a focus, but you only have one. I'm going to just measure some distance here, maybe about right here. And we'll label that as the focus. You only have one focus. And you only have one directrix. And I'll mark that directrix about right here. That directrix, again, is perpendicular to your axis of symmetry. This is our directrix. The other nice thing about working with the parabola is you don't have all four of those values, A, B, C, and D. There's only one value that we have to work with, and that's a directed distance called P. And if you measure the directed distance from your directrix to your vertex, notice that I'm drawing just an arrow headed in one direction here because it's a direction as well. That distance there is P. It turns out that's the same thing if you measure from the vertex to the focus. That's also P. But again, it's a directed distance, so I'm measuring it to the right. If this was opening up to the left, I would be measuring it to the left, which means it would be a negative quantity in that case. P can be positive or negative, depending on the direction that you have here. So there's a sign that goes with it. And if I pick a point, again, that's nice because I only have one value there. I don't have to deal with A, B, C, and D. It's just value of P. If I pick a point, X, Y, on my parabola, and I measure the distance, so let's measure the distance from that point to my directrix. We call that D1, just like we saw with the other two conics. Now there's only one focus here, so I'm only going to measure the distance from that point to the one focus, so that means that's going to be D2, or there's not a D3 here. And that right there is the sketch of our parabola. A lot less to it. A little bit easier to sketch, but it still has some similarities to what we see with the other two conics here that we've already sketched. All right. The last one is probably the easiest of all. In fact, it's probably, I guess, so easy the book actually just left it out here in the explanation of it because it's a circle, and you have the least amount to worry about here with a circle. All right, a circle does have a center right here. We'll label that. It does have a focus. It actually is the same as the center. But there's no directrix. And there's no vertices. So that makes that pretty nice. And there's no A, B, C, and D to calculate. It's just this radius. So if you measure the distance, of course, from the center to your circle, that distance is R, your radius. And in fact, for the circle there, if you wanted to name a point there on your circle and measure the distance to it, you could. We usually don't think of it that way, but that would also be that same distance R. We don't even give it a new name there like we did for the other conics. But if you wanted to name a point, I'll pick a point over here, say, X, Y. And if we measure the distance from that point to the center, that also is R, of course. It's a circle. So this is the easiest one of all to deal with here because of the fact that there's the fewest things to know about it. In fact, we already know probably a lot about a circle walking in. All right, those are the key parts to all four of your conics there. The hyperbola and the ellipse are the two you definitely need to spend a little bit of time on just to make sure you understand all those parts there. All right, let's talk about some of the properties now that we have with conics. It turns out that there's this constant that shows up when you sketch a conic and you measure some distances and actually some relationships between distances and points on your conic. You end up getting this constant that shows up. It's kind of like the same constant we see that shows up when we're talking about the relationship between a circle's circumference and its diameter. That's always the same for every circle, though. Here, with ellipse or a hyperbola, they can vary a little bit, but we do know something about the range they're going to fall into. But this is what it turns out to be. The eccentricity is a constant that defines the conic for us. Once I tell you the eccentricity, you know what kind of conic it is, and you also know a little bit about the shape of it. If you measure the distance from a point XY to the focus, we just called that D2 in all of our sketches on the previous slide. And we divide that by the distance from that point XY to the directrix, which we just defined that as D1 on all of our previous examples there. If you take that ratio, D2 divided by D1, for any point on your conic. That point xy that I marked, you can mark it anywhere you want. If you take d2 and divide it by d1, you get the same constant every time for that conic. And that's what E is. E is that value. That's our eccentricity of the conic. It turns out that there's a relationship then between eccentricity and these two values. We just drew it up above there. E is equal to d2 over d1. You can also write it this way, which is how you'll find it on your form, or in your packet. D2 is equal to E times D1. If I just move the D1 over to the other side, like you see from up above there, I get this little property here. So this is kind of a more common way to see it written. But if you want to think of it in terms of the actual definition of what exactly eccentricity is, the calculation you see up above is the way to think of it. All right, so now what kind of conic do we end up with based on eccentricity? Well, here we go. Your eccentricity, like I said there, will define the conic for you. Move that up. If you have a circle, the eccentricity turns out to be 0. If you've got an ellipse, it turns out that your eccentricity is somewhere between 0 and 1. The closer you are to 0, the more circular your ellipse is going to look. The closer you are to 1, the less circular it's going to look. More elongated it will look in one direction or the other. It turns out if your eccentricity is 1, then you've got a parabola. And finally, if your eccentricity is greater than 1, you end up with a hyperbola. So by calculating the eccentricity, or by knowing the eccentricity, that tells you the type of conic you're working with. All right, there's several properties that I want to go through here with you. With the, in particular, the ellipse and hyperbola, but we'll see some other properties show up as well. But for an ellipse, it turns out that when you measure your D2, this is the distance from your point xy on your ellipse to the closest focus, and D3 is the distance to the furthest focus. When you add those two up, it turns out you end up with 2a, twice the major radius. You can do the same thing with a hyperbola, but you got to take the absolute value of the difference. Now, normally I think of taking D3 as the larger one of the two, so you really wouldn't need absolute value here, but the book writes it this way just to guarantee that this is a positive value. If you take D2 minus D3 and take the absolute value of that, that distance turns out to be also be 2a for the hyperbola. We're going to go through several properties here. We'll talk about the why these are true in the second part of our notes here, but we're going to just talk about each of the properties here for right now. The next set of properties are what are called the Pythagorean properties. And so for an ellipse, it turns out that a squared is equal to b squared plus c squared. Remember that a is the major radius. It turns out that is the larger one of the two, so that's why you've got a squared is equal to b squared plus c squared. Notice it's slightly different for the hyperbola, and that's because the focus is the point that's furthest from the center. So it should make sense to us that in that case, it's going to be a squared plus b squared is equal to c squared, the largest of those values. Those are the Pythagorean properties. All right, your radii and eccentricity properties. This is for an ellipse and hyperbola only again. The two properties they give you in the book there, by the way, are the two that you see on the left. C is equal to E times A. Your focal radius is equal to your eccentricity times your either major radius or your transverse radius, depending on whether we're talking about an ellipse or hyperbola. And A is equal to E times D. That's your major radius A, or your transverse radius A is equal to eccentricity times your directrix radius. The two that you see over there on the right is what you end up with by combining these. I'll show you where those come from here, but I'm not going to worry about looking at the original properties right now. We'll deal with that, like I said, in the second part here. If you take that first property there, C is equal to E times A, and you replace the A in there with the second equation, notice what happens here. You end up with C is equal to E times, and so I'm replacing A with E times D. And so I end up with C is equal to E squared times D. That's that first property I wrote over here on the right. Okay. Now I can do the same thing, but now replace the eccentricity instead. So I'm going to replace the eccentricity in this equation here. So I guess I should solve this for the eccentricity. If I take the second equation and solve for eccentricity, I'd have A over D is equal to E from that. So again, start with the same starting point here. C is equal to E times A. But now replace the eccentricity with what we just said it was equal to. So eccentricity is A over D. So what do we end up with? Well, I have C is equal to, I'll have A squared over D. And you could leave it like that, but up above we got rid of the fraction really. So let's move the D to the other side. CD is equal to A squared. That's where that property right there comes from. Okay, so those two there will be helpful when, depending on what information you're given in the problem, those will be very helpful to help us find the equation of our conic there. All right, that right there is the end of the first part of section 10-5.